Well, hello everyone. I'm absolutely delighted to be able to give this Rosalind Franklin lecture and to be able to reach you in this way, to say something about mathematics and pandemics and us. I was really super pleased and delighted to win the Rosalind Franklin Award in 2020. Let me start by thanking Petra Klapatz and Brian Grenfell for nominating me. Thank you. As you probably know, part of the award is some money we can go and do something with, and I'll tell you more later about our plans for that and maths engagement in schools. But we put our plans together in January 2020, and of course the landscape with pandemics has changed somewhat since January 2020. Indeed, a lot has happened since then. Let me walk you through this. So on the top here I have UK hospital admissions by day from spring 2020 through to essentially present October 2021 as I'm talking now. And you can see you've got this first wave here, which then declines over spring 2020. You've got the second wave in autumn 2020, and I don't know if you call this a third wave or second and a half wave, but alpha variant comes in and causes severe problems in the UK over last winter. Declines quite quickly actually down here, and then you've got the Delta variant comes in and is what is circulating now with this long rumbling wave that we're in at the moment. The other half of this story is of course vaccination. So this is vaccination, and I've lined up the times so you can see them side by side. The top curve is proportion of the whole population who've had the first dose, and then proportion who've had second dose. And vaccine coverage goes up to around 80%-ish at present day out of all people, not just adults. And let's just be clear, the reason we're not looking at a wave this summer and autumn going off the top of the slide, or us being in a really deep lockdown at this time, is down to this vaccination. Right? This has changed everything. Now, over this period of time, I've been part of UK government scientific advice. I've been one of many scientists who've been doing what we can to respond to the emergency and respond to questions which the government asks to help make decisions on policy. Now, it's certainly been interesting times in all senses of what that means. Perhaps I should be a new curse. May you be disease modeller during a pandemic. It's certainly not boring, it's very interesting, but it's also very difficult. And it's a horrible thing to live through. However, being part of the scientific advice, I've been very willing to do that and honoured to serve with what expertise I have to offer and to be part of the community that have done that. However, I want to talk about it in a slightly different sense to usual, rather than the models that went into government advice or on policy decisions there. Because another way to see this pandemic is perhaps it's the biggest science and public engagement opportunity ever. It's something that you can't have been on planet Earth in this time and have not noticed. However, it brings with it lots of challenges and difficulties, right? Because it's a hard subject and it's really emotive and it's difficult, right? So looking at this plot of UK admissions per day, anyone who's lived in the UK during this time, almost certainly one of these pixels is a person they know, or maybe many of the pixels in there. Many of us know someone who's died because of COVID. And this makes it a really difficult subject, but it also makes it an important subject. But this is where I'm going with the us of maths, pandemics and us. This one is very clearly personal. I would also argue that science advice to governments for policy and science communication for public engagement maybe aren't as separate worlds as you might first imagine. Certainly for me, for my own trajectory, they were very much interlinked. I've got 6 pictures here to talk you through some of the key steps along the way for me. For me, it starts back in 2005. I was lucky enough early in career to be a Royal Society University Research Fellow. And part of that, we were encouraged to go on certain training courses, in particular science communication. And I attended this one in 2005, and it was run by Judith Han, pictured there, who was a presenter for Tomorrow's World for many years. Indeed, for many years that I was watching growing up. We always watched this together as a family. Actually, I'm not from a family that's full of scientists. Both my parents were nurses, my mum and my dad. So I started with the null hypothesis that your job doesn't depend on your gender, right? And it came as a surprise to me later that not everyone thinks that way. Anyway, we all watched Tomorrow's World, and perhaps I would say my picture of what a scientist is might have been somewhat shaped by Judith Han and Tomorrow's World. So it was wonderful that she was the one delivering this course in 2005. As part of this, we had various homework to do beforehand. We had to present a short talk while we were there, without slides, which made it terrifying. And we had to write a short article. And we got feedback on both of these. And I'll praise my feedback as maybe not the writing, but maybe talking. And the challenge that we got at the end of this course was to say yes to the next opportunity we're given, the next ask we have for something with public engagement. And it happened that a few weeks later, the next email I got on public engagement was from Millennium Maths Project. Millennium Mathematics Project is based within the Faculty of Mathematics in the University of Cambridge, and I'll say more about them later and some of the links. But of course, I'd say yes to the next thing, so I said yes. And I got involved in 2005 in a series. It was actually a project called Motivate, which was running video conferences between academics sitting in the maths faculty in Cambridge and schools. Well, who'd have thought that delivering material remotely, real-time via videos would be a thing, eh? So this was a very prescient project. And some of these were one-off or two-off video conferences. And eventually we got this idea together for this longer series, working with a few schools. And the idea there was we were working with secondary school children who were then actually designing surveys and collecting data on mixing networks from the local primary schools, and they were doing the analysing of this data. And this photo is here of us in the basement of the maths faculty in Cambridge, broadcasting. Probably can't see, but there's school children on the other end of this. Since then, I've kept long-standing links with the Millennium Maths Project and continue to work with them over the years. And I'll come back with what we're going to do together as part of the Franklin Award. Over the years, I then had lots of opportunities for public outreach and engagement, things like the Cambridge Science Festival. There were one-off talks that appeared and or opportunities to talk to school children, and particularly I would take up anything that involved being able to talk to girls in maths and sort of encourage maths confidence and maybe change the image of what a mathematician looks like. Then in 2014, I was the London Mathematical Society's popular lecturer, which meant I could give some lectures to a large audience, which I very, very much enjoyed. And London Math Society also subsequently made me their Forder lecturer, which meant I went to New Zealand as an exchange with New Zealand Mathematical Society. And I have to confess, I get really nervous about giving talks, and I still do. And yes, even if it's a video talk, I still get really nervous. But one way to learn how to manage those nerves, well, one extreme way, is to go to New Zealand and then give 16 talks in a matter of a few weeks. You learn how to work with it eventually. And yeah, I still get nervous, but the nerves don't feel as awful, and I understand that they can be useful as well. As I mentioned, I take up schools outreach opportunities when I can, and obviously this has not been possible during the pandemic so much. But more on the Lego very soon. Yes, I have the Lego here. There will be Lego. And this takes us through to 2018. Well, it was really 2017 when this starts. And this is the BBC Pandemic, which was it was a TV programme, which was first broadcast in 2018. But it was also a very large citizen science project where through the BBC Pandemic app, volunteers were able to record how they moved over 24 hours and also tell us something about themselves and about who they mixed with each day. And this was part of trying to understand how at that time, or this time, people in the UK moved and mixed. So we'd be able to build better models ahead of the next pandemic. Yeah, and in 2018 I was hoping that would be some decades into the future, but it wasn't to be. The other way to look at it, it was incredibly timely. I mean, the data collection finished in 2019 and we were able to do something with it in time to use it during this pandemic, which was amazing. Here's a bit of filming as part of the BBC Pandemic in a basement in London, and I was looking at a very, very big number. This was the number of deaths for a not real, I should emphasise, pandemic, simulated pandemic with influenza pandemic like parameters and numbers in there. This is the number of deaths we would expect for an unmitigated pandemic, i.e. you don't do anything about it. Actually, as part of that programme, the programme makers wanted us to have a second scenario of a mitigated pandemic, so when a vaccine comes in and saves us all. And actually, we pushed back a little bit against this and said, this isn't what's going to happen. You know, you're not going to have a pandemic arrive and then before the main wave clobbers us, you get a vaccine out. It doesn't work like that. Vaccine production could take, 18 months, 2 years or more before you start to get enough doses to do anything with. And I was very glad we did push back, because what we illustrated instead with that TV programme is what would be the impact of measures to reduce transmission. So if you take action, that means we are less infectious to each other because we're being more careful in some way. We can see what an impact that has as you scale it up across the UK. I'm glad we did that, because actually that was quite close to what the options available were at the time. And of course, vaccination coming in when it did, this was really, really fast still, but it wasn't before the first or second wave. But it was still much faster than any scientist would have hoped for before this pandemic. It's an amazing piece of work. It was actually, the link back to government science here is through the BBC Pandemic, I built a very large, very detailed pandemic model. And of course, it was known then I was very interested in collecting the data for how people move and mix, ready to build better models in the case of a pandemic. And this brought me into contact with a group called SPI-M, which is the modelling group, which contributes to the Department of Health and Social Care in the UK, basically Department of Health and UK government. And after the BBC Pandemic, I joined SPI-M as an independent academic. And of course, SPI-M was the group that was stepped up then into operational mode very early in response to COVID-19 to offer the scientific advice on modelling for the government. So scientific advice and public engagement are certainly interlinked for me, but I would argue they're really not separate worlds in general. It's about being willing and able to translate really difficult ideas for non-specialists, to distill out what's important, being able to communicate, and I'd also say the other thing is being able to work to a very different rhythm to normal academic progress. Right, I promised Lego, so here's some Lego. Instead of giving a more traditional maths and epidemics talk where maybe I show you some equations and show you some different plots of outputs, I thought for this one it might be interesting to show you one of the activities that we use when explaining epidemics to the public, in particular children. Now, what I found is if I present this to adults, actually usually I need to give some rules and explain exactly what I'm doing in advance. But if we're working with children, actually usually we just go for it and just run an example ourselves and explain what we're doing along the way. So today we're going to go children mode. So I have here a bowl of 30 red Lego bricks, and they're all just little standard 2x2s. And this is our population. Each brick represents a person, and it's a population of 30. So I picked the first person to be infected. I'll just put them down here. And every time I take a red brick out, I'm going to replace it with a grey brick, and I have a stash of grey bricks over here. So in it goes. Our population is well mixed, literally, right? So this just means, you know, that they're moving around. People who are mixing with who is different each time. Now, this first person here is infected and infectious, and we're going to suppose for this disease they would infect 2 people each time. So there's one person that infects 2. I pick 2 out, both red bricks. I put them there. I replace with 2 grey. Still 30 bricks in the bowl. There's now 2 who are infectious. They each infect 2. So I pick 4 out. 1, 2, 3, 4. And they're all 4 red still. So here we go. They get infected. Four greys go back in. Now the greys are going back in because they're representing each of these. If they get challenged with the disease again, and they previously had it, then they don't get it again. They've got immunity from previous infection. So keep shuffling. I've got 4 infected now, so I pick 8. Ooh. Ooh. So of my 8, actually 2 of them are grey bricks. So these are people who've had the disease already, so they can't get it again. So it's straight back in the bowl. So I've only got 6 reds now. 2, 3. Of course you could use counters or anything, but Lego's just fab because you can make sort of bar charts as you go. Okay, so there's 6. 1, 2, 3, 4, 5, 6. 6 greys back in. I've got 6 infectious now, so they try and infect 12. Maybe try and infect's a bit unfair, but they challenge 12 people. 1, 2, gosh. 3, 4, 5, 6. 7, 8, 9, 10, 11, 12. Ooh, real mix this time. So what have we got? 5 greys go back in, and the 7 reds come out. Oof. Our epidemic is growing. You want to predict what happens next? So we've got to replace our 7 in the population. Mustn't forget to do that. 1, 2, 3, 4, 5. That's 7. A good mix. The 7 infectious, so 14 I pick now. Oop, 1, 2, 3, 4, 5, 6, 7. 8, 9, 10, 11. 12, 13, 14. Woof, right. Okay, there's actually only 6 reds. And the 8 greys can go back in. 2, 3, 4. Oh dear, epidemic catastrophe. 5, 6. 6 greys back in. Has it turned over, or is this just a low day at random? Now I pick 12. 3, 6, 9, 12. Oh, only 2 reds. Those 10 go back in. 2 reds come out. Replace them with 2 immune greys. Only 2 infectious, so I pick 4 now. 1, 2, 3, 4. Now they're all grey, so that's the end of our epidemic. And there we have it. There's our simulated epidemic for the Franklin lecture. It starts off doubling and it turns over and it comes down quite abruptly, this one actually. Now, this is quite a flexible activity, but there's a lot you can learn from it. So firstly, I don't know if I can show you. Yes, I can. You can probably see there's 2 red bricks left in there. And there's nothing fundamentally special about these red bricks. They could have been infected at any step, but they just got lucky and they weren't infected. And you can make the point, epidemics don't end when everyone's been infected, but just, when they peter out, which can be before everyone's infected. It turns over long before everyone's infected and it starts coming down and can end before everyone's infected. You can connect this back to epidemiological constants like the famous R number. So the R naught of this epidemic was 2. Each infectious person infects 2, not even just on average, in fact exactly in this case. You can change that to be on average by having, say, a dice where you change the faces to be numbers like I do 0, 1, 1, 2, 2, 2, 3, and keep it low numbers so it doesn't get crazy. But the average of those is then the R naught. But then the effective R is the mean number of secondary cases as we go in the epidemic, and that gradually turns over. It goes less than 1 when the epidemic comes down. So there's a lot you can talk about with this. And of course, the concept of herd immunity is very, very visible with this. There are people that could be infected in there, but just the way the mixing patterns work means that if there's enough other immune people, then they're protected because the epidemic ends. Now, when I've done this before with primary school children, in fact, the last visit I did before the pandemic, some of the girls finished before the others, so they decided to modify the activity for themselves and try it with vaccination. So they thought, you don't just let epidemics go, you do something about it. So rather than starting with 30 susceptible people, they modified to have 30 who are susceptible and 10 who are vaccinated, or some who are vaccinated. And then if you pick out a vaccinated person, then they don't get infected. They go straight back in, like the greys. So then you can see how this modifies the epidemic. If you do this repeatedly, or you've got lots of people, I've made some more to save you having to watch me do this repeatedly, you get, with the same rules, you get different runs and different dynamics. So this one in the middle just has a higher peak. It was a bit spikier. Actually, these end ones are, oh gosh, very similar. They're not exactly the same. This one comes down very abruptly. The one we just did, this one comes down a little more stepwise. So you get these different patterns. There's a limit to how far you can push this activity, but the point is doing it. You get this conceptual picture of how epidemics work. You could imagine running this with a lot more Lego, and needless to say, I have a lot more Lego, but I'm not going to do a big one here. But maybe in a classroom you could, and see what goes on. You can talk about ideas in terms of this. For example, very much in our minds now is the idea of waning immunity, right? So someone who's immune might not stay fully immune forever. They might gradually become susceptible again. Well, we don't have colour-changing Lego bricks, but you can imagine it as the greys slowly go red again, and then the possibility of a large epidemic can happen again. You can talk about boosting, changes you back to grey again. Of course, the whole idea of immunity, or your immune state, is really a function of which variants we're talking about. If we're running with one variant, maybe there's one state, but if we are running with a different variant, maybe we need to change some of those greys if the variant escapes prior immunity. So you can talk about all of these ideas, and of course, perhaps most important, you can talk about it, it's not just one population, right? So it's going to be lots of populations. You can imagine loads of them joined together and think about what that would mean for the dynamics. So there we go. There's an introduction to epidemics using Lego. Okay, the Lego is mostly tidied away, and I'm now back in my box just to finish up this lecture. I'm excited to tell you a little bit about our plans for the Franklin Award. This is working together with Ems Lord and Julia Hawkins from the Millennium Maths Project. We've come up with this plan. We're going to develop and release materials for lessons for Key Stage 3 school students. That's roughly age 11 to 14. And this is to connect into directly into curriculum topics, from curriculum topics to the dynamics of infectious diseases. Now, this is a little different to some of the outreach that I've been talking about, as rather than being some additional bonus activity, this is going to be very much curricular. We want it to fit into the mathematics lessons that these students have. We hope this means we'll reach a wider audience, but we hope also this means it will show the importance of the curriculum that they're covering and to put it into a wider context as well. Why Key Stage 3? Well, that's a group we've had success with before, with the Motivate video conferences. We know this can work with the ideas from epidemics. And it's also a time when school students are thinking about how they fit with mathematics and science generally. And to be blunt about it, it's also a time when a lot of girls decide that mathematics or science somehow is not for them. So I'm hoping with a project targeted at this age group, we can have some impact in this group and help to change things, really. We're thinking mainly about UK curriculum, and it's UK schools we're aimed at, but everything we do will be available, so there's no reason why it can't be used elsewhere in the world as well. Now, I mentioned that we are still working with Millennium Maths projects through the pandemic, and it's through this consortium. It's the Juniper consortium. Juniper is short for Joint Universities Pandemic and Epidemiological Research. And essentially it's a consortium of lots of research groups of infectious disease modellers. We've very naturally come together to pool our efforts in terms of urgent work on COVID-19. And we found we work very well together as a consortium, so we want to continue this into the future and as preparedness for maybe future emergencies as well. There's a picture there of the 16 of us who are principal investigators and co-investigators of Juniper, essentially the heads of the research groups. But Juniper's much larger. It's also many other researchers and staff who are involved as well. The thing I wanted to highlight with this here is the scientific writers. Right, you can see we've got Rachel Thomas and Marianne Freiberger working very closely as part of Juniper, and they are the editors of Plus magazine, which is part of Millennium Maths Project. The idea here is having expert scientific writing very much as part of us means there's a very live dialogue between the latest research, what the conundrums are we're thinking about, what's just come out, and communicating it to the public through science writing. And if you want to read more about what we've been doing, you can follow the links there below, plusmaths.org/juniper. But this is a new way of working for us, to have science writing sort of so built into what we're doing as a consortium. And it's been in response to the emergency. I think it's been absolutely right for the need to communicate during this research, during this emergency from research world to public. But having got used to this, I think this is how a good scientific consortium should function in the future anyway. I absolutely love it and want to keep it for the future. Okay, finally, to wrap up, many thanks to a lot of people for the things I've talked about here. For the Franklin Award nomination, Petra Klepatz and Brian Grenfell, thank you. And for developing these plans to Ems Lord and Julia Hawkins. Yes, our plans have been delayed with the pandemic, but I think possibly more important and potentially more impact for them when we get there, linking this back to school mathematics. On the left, bottom left there, I've listed the Motivate video conferences squad, and on the right, the BBC Pandemic squad. And thank you very much for listening, and I look forward to your questions.
Well, thank you, Julia, so much for a wonderful lecture. I especially enjoyed the Lego. Very informative. I'd remind the audience to type their questions into Slido and also to abide, of course, by the code of conduct. We have a first question here from Alex Wood, who asks if you can give more detail about what new things you learned from the BBC pandemic work.
Alex, thanks for that question. I could give a whole other lecture on that, but I won't. So some of the hype, actually, let me back up. The timing of this is we got the data sort of late 2019 and we were working on analysing it in early 2020 when all of this happened. So some of the analysis has happened in parallel with the start of the pandemic and some of it's gone on hold. But we were able to pick out what we needed most urgently. There are a few papers and preprints out with some of the work from it, but the key things were firstly the age-structured mixing matrices. What we were using before came from actually a wonderful study called Polymods, but it was A, limited in size, it's a few hundred rather than tens of thousands, which we had in BBC Pandemic. And also it was a while in the past, and the way particularly what we found was younger adults and teenagers mix has changed quite a lot over the last 10, 20 years. Older adults, maybe not so much. So getting that updated age mixing matrix so we could use that has been important, and to understand what the limitations of the past studies are. The spatial structure, we've used some things from that, though that's been less essential in later stages, well, after the start of the pandemic, but there's more to be done there. And the other thing that we've done that's been very much on my mind from that is we've learned a lot about how to do these studies, right? So there's a lot of talk now about putting more studies together in the future to understand mixing and moving patterns, particularly live during pandemics. And we learned a lot about maybe what not to do as well as what to do. And also the difference between what people say they do in terms of travel and movement and what they actually do according to their phone's GPS. They aren't quite the same. So sort of the Rosetta Stone between surveys and GPS surveillance that way. So that's some of it, but not all of it yet.
Yeah, clearly you could go on for a whole lecture. We have a question from Larry Clark. Where can a member of the public get epidemic source data so we can do our own modelling?
So for the UK and the government dashboard, which I mentioned, coronavirus.data.gov, actually is pretty amazing. You've got to click through a little bit to get the nice downloads, but you can get data split up. Sorry, I've got something popped in my window to move that. You can get data split up by day and by location down to quite a fine scale. And that should be more than enough, even for professional modelling, yet alone as an amateur. I would take sort of the aggregated data by day as a place to start, just to visualize it and get used to working with it. But there is quite a lot out there in terms of the case data.
Great. And then one from Jeffrey Greenspan. How does the fact that a pathogen's transmissibility can vary impact mathematical models of pandemics?
Okay, Jeff, there's a lot in that. So there's varying over the time of one person's infection, right? So the moment I get infected, I'm not infectious. I mean, the Lego cubes, right? They're sort of, if we do it step by step, of course, it all happens continuously through time. That sort of profile of how infectious you are against time can go straight into a mathematical model. Indeed, the BBC pandemic model, what I had in there was flu-like parameters. So nothing on day 1, a little bit on day 2, quite a lot of infection on day 3 and day 4, and then tailing off day 5 and day 6. So you can put that in by having time-dependent models. But Jeff, I suspect you're getting at also not only varying through time, but varying in other ways. And perhaps different stages of the pandemic, different settings, different places across the world. Yeah, that starts to get tricky. It certainly does. Maybe the side of that means this is difficult is that for a lot of the pandemic modelling, I'm just talking about in general, not just my own work here. You're trying to get parameters and understand how coronavirus spreads, and you use studies from one country maybe on this is how infectious you are on different days, and you're applying it to different countries. And we are largely making the assumption that in the absence of other information, it does just translate the same way between different settings. And that is a problem, and it is a limitation the whole time, that we don't know exactly that this does apply between settings. So, good and subtle point, Jeff, thank you.
And then there's an interesting question from Tom Irving about what you learn from the past. What advice would you give your past self when you started your career, and then later at the start of the pandemic?
Tom Irving, thank you for that. What advice would I give my past self at the start of career? I'm not sure when you call start a career. Is it uni or after uni or PhD? What I would say to someone starting is follow your interests, right? If it's interesting, it engages, and your brain is drawn into it, it's a good reason to pursue it. I found epidemics and pandemics just something that gripped me. And that was the reason I went towards it. Sometimes your mind just tells you the right thing, go for it. Start a pandemic, oh my gosh, I would have told myself so many things if I could just send myself a memo back in time. The top personal one, we just have the confidence to help, because even if I'm feeling the whole time, it's frustrating, because if we could do these models for an extra few months, they'd be better. And it's frustrating. We don't have this data, we don't know that, and we're guessing at this. But being able to contribute something quickly is worth it. And I don't think I grasped that at the start. I was quite hesitant and unsure that I had something useful to contribute, but found gradually over time that I could. And I've seen others go through this similar cycle of knowing that we can do something useful here.
And then one from Michael Ajao Olarenoi. What effects does quarantining have at the beginning stage of the pandemic?
Well, as I mentioned, really early in the pandemic, the only control measure you've got are things that reduce the transmission between people by changing their behavior in some way. So quarantine would be one of those. Advice on you test positive, you stay at home. But by quarantining, I'm not sure if you will mean everyone goes into a full lockdown, and we now know exactly what that does. Having seen that happen in many countries now, it's incredibly effective at stopping a pandemic in its tracks, but it will bring things down gradually. It doesn't sort of drop off suddenly. You know, the cases have got to come down over time, so you want to do it early. And then there's the effect of individuals. If you know you've got coronavirus, you obviously take yourself out of future transmission chains. That's been limited because, of course, lots of people can be infectious before they know it, or infectious without knowing it. So it's hugely valuable, but it's not the complete solution there. Michael, I hope that's answered your question. I wasn't sure exactly which bit of that you were asking.
And from Andrew Planet, are children being taught about pandemics at an earlier stage to increase protective measures such as social distancing to avoid pandemic debacles in the future?
Well, never mind children. Perhaps adults need to learn some changes in behaviour. So I'm stepping well outside my field on human behaviour here. But the masks is an interesting one, isn't it? I mean, how many of us wore a mask when we had a cold in the winter before, or we had flu in the winter before, or would go on the London Underground and wear a mask just because it's flu time? We just didn't in the UK, right? And now we've got used to it a little bit. So I wonder if, never mind children, perhaps we need to learn that this is a useful thing to do. The children, I'm not sure they're being taught about pandemics in order to, protect them explicitly in the future. They've been taught about it because they've had to live through it. And without a doubt, some of the worst effects of this pandemic, both in terms, well, the overall effect of the pandemic on children, I think, has been absolutely horrific in this country. And it's largely for measures that have needed to be in place to stop transmission among the whole society has affected children. So it's really important that children understand as much as they can about the pandemic, and that, you know, we're honest with them about what happened. And as I say, we've got this window where it's important to explain to them what's happened in the pandemic, how pandemics work, and what could be ahead. So it's a valuable time, but with it difficult as well, because we know they've suffered for it.
And then following on from that, from Philip Wedmore, did your work with children help when you were explaining the modelling to our politicians? How do you convince people to accept findings which are counterintuitive?
Oh, Philip, that's a good question. Yes, I think is the answer to did it help. If you can explain it, if you can't explain it to a child, right, there's something wrong. We haven't learned how to explain it well enough yet. I mean, I haven't yet turned up to a SAGE meeting with one of these epidemics in hand, but maybe one day. Being able to explain it lots of different ways, learning to re-explain it outside of our language of mathematics and equations. You notice I showed you 0 equations in this talk, which is not something I probably could have done without doing lots of outreach work and learning how to rethink about it again. So yes, it certainly helped in learning how we think about and communicate it. Was that the full question? What was the rest of that question? Sorry, Eric. Oh no, it's. I hope that answered it. It certainly helped.
Yeah, no, that's good enough. From Alex Wood, can you comment on why the UK initially followed a strategy of herd immunity, unlike other countries?
I think that's outside of what I can answer in this one. That's getting to the politics and the decisions at the time, rather than the epidemics and the science there. I mean, one comment I will be drawn into is there is only one way out of this pandemic, and that's immunity. Whether that immunity has come from natural infection or vaccination, let's not kid ourselves. Staying in lockdown forever and waiting for it to go away would have taken centuries, and obviously there's other problems then. There was no way out of this except immunity, and looking ahead, there is no way out of this until we're all out of this as a planet, right? So there's no other solution. It's horrible. And there's tricky things ahead, but immunity from some source is the only way.
With hindsight, what do you wish had been modelled or changed about the models that were run early on in the pandemic?
Okay, a lot of the work done early in the pandemic was absolutely heroic, nothing short of the timescales it was done under the limited information. The hindsight, and actually, to be honest, we sort of half knew this at the time. Our picture of a respiratory virus pandemic was very much based on flu. I mean, the group I was part of and am part of, SPI-M, is the I is for influenza. So in some sense, we were very biased by what influenza is like. And COVID is not influenza in many different ways. And gradually, you know, we learn about that and modify that. One of the biases is with influenza, transmission in children is super important. And it's taken a long time to understand exactly what role children play in COVID, especially early in the pandemic. It's different now when most older age groups have been vaccinated. But early in the pandemic, it was hard to estimate their role. And our minds were very much in flu. And I think all of us involved now are thinking our preparedness and our planning for the next pandemic, are we just making more COVID models, or is it something we can't imagine? Or will the surprise be it's actually COVID again, or it's flu or something? But it's understanding we can be biased by thinking about past pandemics a lot.
Well, unfortunately, time has passed. There are lots more questions that people would like to ask, and myself included. But thank you so much for a wonderful lecture, and congratulations on the award of the Rosalind Franklin Medal. Thank you all for attending. Let me tell you that the next Royal Society lecture will be the Milner Lecture by Professor Garamani on the 10th of November. Thank you so much.